Ever feel like some functions in math are hiding something? Well, today we're going full-on detective. We're investigating a family of functions, the inverse hyperbolics, and we're going to expose their secret identity. Turns out, they're not what they seem. They're actually logarithms in disguise. And knowing that secret, it makes them way, way easier to handle.
Okay, let's meet our first suspect, the inverse hyperbolic sine of x. I mean, on the surface, it looks pretty familiar, kind of like its cousin, the inverse sine function. But what is it really? Let's peel back the layers and see what's lurking underneath.
All right, time to crack open our first case file. Our mission is to take this function, inverse hyperbolic sine, and figure out its true logarithmic form. We're just going to follow the clues step by step. Let's do this together. So, every good investigation starts with laying the groundwork. First, we just set our function equal to y. Simple enough. Then, we use what we know about inverse functions to flip it around, giving us x equals the hyperbolic sine of y. And now, here's the critical move. Step 3. We swap out sin y for its real definition using exponentials. This right here is the key that's going to unlock the whole mystery.
Okay, now for a little bit of algebraic shuffling. First things first, let's get rid of that fraction by multiplying both sides by 2. Easy. Then, and this is the big move, we multiply the entire equation by e to the power of y. And look what happens. That e to the minus y times e to the y just turns into 1. That's exactly what we wanted to happen.
Let's just rearrange these terms, get everything over to one side, and... Wait a minute, does that look familiar? We've got something squared, minus a multiple of that same something, minus a constant. That's a quadratic equation. It's not a quadratic in x, no, it's a quadratic in terms of e to the y. This is our aha moment. The case just broke wide open. And you know what we do when we see a quadratic equation, right? We don't have to reinvent the wheel. We just bring out the big guns, the reliable, the powerful, the one and only quadratic formula to solve for our variable, which in this case is e to the y. So we plug in our coefficients, we simplify a bit, and here's what we get. Our term e to the y equals x plus or minus the square root of x squared plus 1. But hold on a second. See that plus or minus? That's a new puzzle. We've got two potential answers, but a function can only give us one.
So now we're at a crossroads in our investigation. Which path do we take? The plus or the minus? We can't just guess. We need to find one more piece of solid evidence to make the right call.
And the final clue comes from a fundamental truth about exponentials. The function e to the power of anything is always, always positive. It never hits 0, it never goes negative. But if you look at that second option, x means the square root of x squared plus 1, well, that expression is always negative. So we have to throw that solution out. The only logical choice is the positive root. So with our choice locked in, we have e to the y equals x plus the square root. Now to solve for y, we just take the natural log of both sides. And there it is. The secret's out. The inverse hyperbolic sine is really just a natural logarithm. And this form is often so much easier to use, especially in calculus. Case closed. But just when we think we have cracked the code for everything, the investigation takes a turn. Our next suspect, the hyperbolic cosine, or cosh, has a little twist that makes things just a bit more complicated. So here's the problem. The hyperbolic sine function is what we call one-to-one. Any horizontal line you draw only ever hits the graph once. Easy. But hyperbolic cosine? Look at that U-shape. It fails the horizontal line test big time. That means you can have two different inputs, like 2 and -2, that give you the exact same output. And that makes finding a single inverse tricky.
So how do we deal with this? Well, mathematicians came up with a pretty elegant fix. We just restrict the domain. We basically make a deal to only look at the right half of the cosh graph, where x is 0 or bigger. By just chopping off that left side, we force it to become a one-to-one function, which means we can actually define a proper inverse for it.
Okay, with that little restriction in mind, we are ready to open our second case file. Our target is now the inverse hyperbolic cosine. We're going to use the same detective methods as before, but be warned, this case has a little surprise waiting for us at the end. We are on a very familiar path now. We start with x equals cosh of y, we substitute in the exponential definition, multiply and rearrange things, and just like before, it beautifully simplifies into a quadratic equation in terms of e to the y. So once again, we reach for our trusty quadratic formula. And here's what we get.
I mean, it looks almost identical to what we got for the synth case, right? There's just one little minus sign changed under that square root. But that tiny change has a huge consequence for our next step. So here's the twist. Last time, it was easy. We had a negative solution we could just throw away. But this time, for any valid input for x, both the plus version and the minus version give you a positive number. Our old clue that e to the y has to be positive doesn't help us choose this time. So, what does that mean? We need a new clue, and we find it with this really clever algebraic trick. Look at that minus solution on the left. If you multiply it by a special form of 1, in this case x plus square root of x squared minus 1, over itself, the top part simplifies perfectly to just the number 1. It's a neat little trick that reveals a secret connection between our two solutions. So here's the punchline. That minus solution is just the reciprocal of the plus solution. And if you remember your log rules, the log of a reciprocal, like the natural log of 1 over a, is just the same as the negative of the original log, or minus ln of a. And that's why the full solution has that plus or minus out front. The two answers, one positive and one negative log, correspond to those two original inputs, like a positive y and a negative y, that gave us the same cosh value in the first place. Now, by convention, when we restrict the domain, we just agree to take the positive log solution. So, we've cracked the case for inverse synth, and we've cracked the case for inverse cosh. We've uncovered their secret logarithmic identities. But this investigation isn't over. Now, the last part of the challenge is all yours. Here's your task, your mission, should you choose to accept it. Using the exact same methods we've used twice now, start with the definition, substitute the exponentials, and work the algebra. See if you can prove this logarithmic identity for the inverse hyperbolic tangent. The algebra is a little different, but the core strategy is exactly the same.
You know, what this all really shows is that in math, things are rarely what they seem on the surface. There are all these hidden connections, these secret identities just waiting for us to find them. The only question is, now that you have the tools, what will you uncover next?